So variational autoencoder introduced some constraint on latent space so that the latent space here, latent value here, follows some normal distribution and zero mean and identity covariance matrix. Okay, so for the variational autoencoder, there is one more clear objective. We want to make the latent variable z generated from all your training data point x1 through xn follow some normal distribution. Okay, and also like as before, we want to reconstruct x1 hat, x2 hat to xn hat that is very close to the original input x1 through xn. If we can satisfy this target latent variable distribution, then basically from the decoder, when you randomly generate a normal latent variable, and when you give the normal random variable to here, then you can easily generate a new image. Because here we give some meaning to the latent variable space so that all the area having very high probability for the normal distribution is more likely be mapped to real image, because we have some constraint on the latent space. When the latent variable or latent vector satisfy the constraint, then it becomes the corresponding output for the decoder is more likely real image, looks like real image. Okay, so this is the target of variational autoencoder. So let's go to more details. So here there's encoder part. With parameter, let's say pi. There's decoder part with parameter theta. Here, input xi come to encoder, and the encoder in this case generate mean value, which is function of pi with input xi, and the covariance matrix information sigma pi. Usually the covariance matrix is a diagonal matrix, so we ignore the correlation between two latent elements. So the encoder output is mu and sigma, and we assume that the latent variable z is not deterministic vector, but a random vector that follow the mean mu pi xi and the covariance matrix sigma pi xi. Okay, so we assume z follow normal distribution mu pi xi and sigma pi xi. Okay, and from this distribution, we randomly generate the latent variable z. Okay, and then decoder, again, decoder as well, make output. The output is mu sigma z and mu theta z and sigma theta z, which define a normal distribution, and we assume that the corresponding output x follow a normal distribution with mean mu theta z and covariance sigma theta z. Okay, so why this is useful? First, we can measure the distance between this latent variable outcome, so the output of encoder and their normal distribution with mean 0 and identity covariance matrix. Why this is required? Because we want to make our latent variables follow zero mean and unit identity matrix covariance matrix over whole entire data point. It is very important to assess how much current latent distribution close to zero mean and unit variance case. If the distance is very high, we have to do some effort to make your latent variable distribution to be close to the normal distribution with mean 0 and identity covariance matrix. So here, from this distribution, we define a loss function for the encoder part using KL divergence. KL divergence between, let's say this distribution is q pi z given xi, okay? Because it is very, I'm very lazy person. I don't want to write down full characters. So let's say q pi z xi is the normal distribution with mean mu pi xi and covariance matrix sigma pi xi. So for the encoder, we define a loss function. The loss function is KL divergence between q pi z xi and normal distribution with mean 0 and identity covariance matrix. So here the encoder part will try to minimize this KL divergence for each data point xi. So I from 1 to n. Okay, so this part is kind of forced to make your latent variable distribution follow normal distribution with mean 0 and identity covariance matrix. And here, for the decoder, we define a very natural loss function, which is negative log likelihood value. So we want to minimize the negative log likelihood value for decoder, which is maximize the log likelihood property. Okay. So since the latent variable is random variable, follow q pi z xi, we will take expectation for the negative log likelihood value. And the negative log likelihood value is this p theta. So let's say this is p theta distribution for xi and given z. So compute the probability for point xi for this given z using this normal distribution. Okay, so this is the probability value at point xi, at the input xi, when the distribution follow this. This comes from the latent variable z, the given latent variable z. So I will use this notation p theta xi given z. So basically decoder just maximize your likelihood value, and since latent variable is random variable, we take expectation for the likelihood.